better. Okay, so welcome back. We've got Alex Titterton now from Graphcore. Thank you, Alex. Are you okay to take over?
Yes, thank you. Hopefully you can all hear me pretty well on Zoom as well. So yes, I'm from Graphcore. We're a UK-based chip company, make a chip called the IPU. Not all of you will necessarily have heard that much about it, or at least if you've heard the name before, you might not know what it is, how it works. So I'll go through sort of who we are and what our game is, and go through a little bit of some of the hardware and the software, where we think some of the interesting research is going, some of the challenges of current and future AI. We all know it's not going to get easier, it's going to get more difficult, and what we think we can do to address that. And then towards the end, whilst everyone's stomachs start to rumble, I'll try and be as quick as I can to not hold up lunch. We'll have a quick look at the crystal ball, at least the heavily redacted crystal ball that I'm allowed to tell you about what the future is from our side, our kind of offering, and how we think that's going to open up some nice doors and research avenues that wouldn't otherwise be available. So what do we do? What do we do at Graphcore? There's a few different architectures out there, different types of chips for different purposes. We all know about CPUs, GPUs, if you're familiar with. CPUs exist as well, sort of a bit more vectorized processing compared with CPUs. CPUs really, to a certain extent, is a GPU with some knobs on. It's the similar kind of architectural principles, but with different kind of memory hierarchies, rather than being a completely different architecture. But compared to the CPU, they're both quite different. And then we're going to introduce the IPU, which is very different again for different types of applications, sort of designed from the ground up. So comparing different types of things. So Graphcore, of course, making the IPU. Start with the CPU. Anybody who's built a gaming PC will be quite familiar with the whole having all your memory in separate slots off the chip on the motherboard. Typically, these are designed for scalar or not all that highly parallel processing, unless you've got lots of CPUs in a big cluster, of course. But typically on a single chip level, it's general sort of scalar programming. And then your memory is large, relatively cheap, but off chip, the bandwidth isn't so high. And generally your energy costs associated with getting sort of per byte of data from your memory is quite high. So when we get to kind of accelerated programming, we go typically towards the GPU, that's the most well known. We go into what we call vectorized programming. So it's parallel, you can do lots of things at once, but really you can do lots of the same thing at once on different bits of data, which, considering what GPUs are built for, that makes a lot of sense. You're doing graphics, you're doing some kind of shadows projected in a 3D rendered scene. The maths is basically the same for every pixel. You just want to do it on lots of bits of data at once. So you've got memory that's a bit closer to the chip, still off chip, the vast majority is, but it's closer and faster compared with sort of DDR for a CPU, and you've got a vectorized sort of capability in the processor. So typically we're looking at about 2 terabytes a second for the highest end A100, and similar for the H100s when they're coming out, if you can get one. The kind of bandwidth, so it's still it's pretty high, but it's still off chip. You've still got lots of cores queuing up to get access to data off the chip. So what we do with the IPU is we take sort of this parallelism and the memory architecture to the extreme, and we instead have lots and lots of cores, almost 1,500 cores on a single chip that are completely independent. So it's like having, in effect, 1,500 single core CPUs with a little bit of memory each. They're completely independent. There's no performance penalty, whether they're doing all the same operations as each other or different. And then we have lots of memory on the chip. So rather than having sort of 10, 20 meg of your cache, we have 900 meg of this same kind of in the silicon memory distributed physically across the processing cores. So lots of cores doing the same or different operations on different bits of data, all working in a little sandbox on their own local bit of data, a little bit of memory, so they're not queuing up behind each other. So then we have, rather than 2 terabytes a second, more like 65 terabytes a second, sort of all hammering their own local cores, and then they can talk to each other as well. We'll go into sort of the kind of the software architecture details in a moment on how we stop things going wrong, because of course you've got that many cores running at once. It'd be very easy to have, if in a complete free-for-all situation, it would be quite sort of anarchy, really. You'd have lots of cores trying to write to the same place and all these sort of things going wrong. So we do have ways of handling that as well. So the idea is much higher bandwidth, smaller memory, admittedly, compared to, say, 80 gig of HBM, but the idea is you use it a little bit differently. What's one of the main kind of benefits? Well, for example, with a GPU, you've got a large neural network. Not what it was built for, but it's better at that than the CPU is typically. How do you make it go quickly? Well, what you want to do really with a GPU is lots of the same operation at once. The simplest way to do that is to have a very large batch size. So you're running over lots of, say, images or sentences or whatever it might be, all at the same time. There's downsides to that. Some models, you want to be able to do lots of weight updates. If you can do a small batch size, update the weights a bit, and then rinse and repeat more often, it might train sort of better at kind of subtle features, things like that. Whereas if you go over 1,000 images before you do any weight updates, you might be missing certain subtle features. Other reason you like a large batch size on a GPU is you've got off-chip memory, relatively high latency. So if you can grab lots of data infrequently, that's better than small amounts of data more frequently. If your data's on the chip, none of this really matters. You've got single cycle memory latency, and we can do different operations at the same time. So we can get good results at batch size 1, which in some cases then gives you really good throughput, but also you might find you get the same kind of accuracy with training for fewer number of epochs because you can update the weights in a much more kind of fine-grained and subtle way. So there's lots of different benefits there. Admittedly, there are other trade-offs, of course, with 900 meg is big for SRAM, but it's not big compared to off-chip memory. So there are going to be situations there where a model is larger, so you hit that limit of now I need to use more chips earlier than you might do on certain GPUs. So admittedly, there are, of course, trade-offs there, but it's trying to open up the avenues of research that we don't try that because it doesn't work well on GPUs. Isn't really a good enough reason not to try it. Can't there be some hardware that can open that avenue up again, which is what we're here to provide. So a little bit about the chip itself. Rather than just going smaller and smaller nanometers in the fabrication process, we've taken a different approach. Instead, we stack wafers on top of each other. So you start off with the circular wafer, quite white to circular wafer that you then chop up into squares. Does sound rather wasteful, but that's how it's done. Before we chop the wafer up into lots of different chips, we stack 2 together so that the wafer on the top is the logic, so where all the compute's done, and the wafer on the bottom is for power delivery. We'll get onto details of that in a moment, but the main suggestion that is much more efficient power delivery to the chip rather than just having all your power delivery capacitors around the very outside. As I say, 900 meg SRAM, almost 1,500 processing cores. Each of those has got 6 threads as well, so we've got nearly 9,000 threads running at once. Huge memory bandwidth, and designed really for the kind of the newer kind of challenges in AI, again, which we'll go on to in a moment, as to what kind of thing the IPU is better suited to than other things out there. But this 3D wafer on wafer, and this we think is a much more efficient way of doing things rather than shrinking the fabrication the granularity, is because when you go down to 4, 3 or smaller nanometers, your power usage is going to get quite high. The heat becomes more of a problem. If you can stack, you can sort of minimize those. Obviously, at some point, you do start getting a lot more heat as well, but typically the scaling is a bit better for that. But also, as we say, we have our power delivery die. This is upside down because you've got the silicon bumps there. That would normally go on the motherboard. But your power delivery capacitors and then the actual logic die there, rather than having these in a ring around the outside. What it means is the volt drop isn't as bad. You can turn the clock speed up by about 40%, and the power usage is the same as the previous version of the chip, which in every other respect was identical in terms of the number of cores and everything else, just that it wasn't this 3D version. So in effect, this newest version of the chip has 40% clock speed for free. No more power usage. In fact, the power usage is more stable as a result of this. Interestingly, these they're called deep trench capacitors, high capacitance, tiny bits of silicon. They're actually just DDR memory. That's exactly the same silicon that you used to make DDR memory. It's just a very, very high capacitance capacitor in effect. So we use that to make the power delivery layer and stack them on top of each other. And we think this is a better way to go in the future as well. We can stack more logic dies on top of this and go bigger and bigger. TSMC is where everything's made, and no one else in the world can do this anyway. So we're partnering quite closely with them. Other nice benefit is if you want to build a chip, say you have a brilliant idea for a chip and you want to use 3 nanometers, best of luck, because Apple have bought the entire 3 nanometer queue for the next however many years because of their iPhones. 4 nanometers and 5 are pretty much chopped up by existing GPUs from AMD and NVIDIA and so on. So actually, if you don't have to go down to tiny nanometers, you can have TSMC at your beck and call, asking you very nicely to please use our machines that otherwise no one's using. So in that sense, everybody wins as well. So we shouldn't have the same supply problems as H100s, of which I've still never seen one. So apparently they're out there somewhere. So the hardware is all rather fancy. That's most of the silicon kind of view of things. But the idea is we can have much more flexible parallelism. You don't need to vectorize. So we need some software to go with that to allow people to actually use it. So at the low level, we've got all our kind of specific drivers and that sort of thing that the user doesn't normally have to really worry about so much. But we have a low level of the software stack called Poplar. This is kind of analogous to CUDA. Sorry for swearing. But of course, CUDA is proprietary to NVIDIA GPUs. Poplar is proprietary to IPUs. The idea is it's your low level C++ in our case framework to let you do sort of pretty much whatever you want. So you set up your main kind of program there. You can have the individual single-threaded applications that run on individual threads on the IPU, and then have lots of that template or lots of different ones all running at the same time. You can manually say, put this slice of a tensor on that core and all this kind of thing. As you go to the higher level, we have sort of libraries on top of that for things like matrix multiplication and so on, linear algebra type libraries, neural network type functions. That you can then use to write an application without having to do everything manually yourself. Some of the memory mapping starts to become the compiler's problem, not your problem, but also that forms the back end for the high level frameworks. So for the vast majority of users, realistically, they're not going to want to do C++. They may well want to start off with Keras and TensorFlow, or they might start off with PyTorch or something like that. So we have these frameworks supported at the top end as well. As I say, behind the scenes, everything goes through our software stack. So it might look like TensorFlow or PyTorch, but it's not targeting CUDA, it's targeting Poplar. But that, again, takes a lot of that kind of burden off the user, makes things easier to get to work with. A couple of things to note in terms of how it works. So we've got almost 9,000 threads running at once, lots of different bits of memory. That's going to be a nightmare to dispatch dynamically, sort of operation by operation. So we don't do that. We build up a computational graph that represents maybe a forward pass and a backward pass of our model or whatever algorithm we're running, and we compile it. So we have a static computational graph. We fix the size of the tensors and that sort of thing, and then we just compile it. So once you've compiled this big executable, every training step is just a call to that executable. So we helps us boil out a lot of the inefficiencies. Also helps make good use of the fast but not enormous memory, and keeps things very efficient there. And of course, we've got plenty of software examples online that users can use to get their models running. Typically, as with anything, the lower level down the software stack you go, the more work you would need to do to port it. So go from CUDA to Poplar or anything else, really, of course, it's going to be basically a rewrite. But if you're going from TensorFlow on a GPU to TensorFlow on an IPU, you wouldn't have to do much in the way of code changes. There might be some design choices if you've optimized for this processor and now you want to try that one. Some design choices might differ, but generally speaking, the idea is it isn't, you're not rewriting your code, you're not having to do everything differently. You should be able to just get on with it. Right, so a quick look at some of the research collaborations we've been doing so far, some of the interesting themes that we've started to pick up. Then we'll go into where we think the world is heading, where some of the interesting things that are coming up that we've worked on ourselves and also observed from some of our research partners, both in industry and in academia. And then we'll have a quick look at the future before everybody starts throwing things at me to stop so we can have some lunch. So we're very happy to have been able to support a lot of research collaborations, and we certainly encourage universities and projects to work with us as well. This project included, but even beyond that, certainly we can offer lots in the way of collaboration. We've had some nice stories already. It's quite old now, but some nice papers with the Bristol and CERN particle physics teams looking at different aspects of where they're introducing machine learning into kind of not just data analysis scenarios, but also generating realistic looking simulated data. So using GANs to replace or at least to augment Monte Carlo simulation, things where you can simulate it well with Monte Carlo, but it's very, very slow. So can you accelerate that? But even cases where certain physics objects in a collider actually, to first order, they're very easy to simulate, but once you get to more intricate kind of properties, it's not all that obvious, and it certainly can't be solved analytically either. Can things like GANs better learn kind of to represent substructures of various high energy physics objects in a way that they can produce realistic looking data that's more realistic than a simple simulation can, and also much, much quicker. So things like that as well. Similarly, the general AI HPC crossover is certainly of big interest. So we've talked a lot yesterday about surrogate models and all sorts of data-driven approaches versus augmenting traditional approaches and so on. that we certainly see as being a big factor as well. It's not necessarily always going to be the case that you'll naively just replace everything with one massive machine learning model. It might be that actually this bit here is data movement and data processing. That doesn't really make sense to replace with a model. It's this bit in the middle here. This is the bottleneck, and it's some huge calculation that is very, very hard to do. Sometimes just replacing the right bit with ML, and maybe it starts there, and then you start thinking, actually, as things advance, we can replace a bit more and a bit more. Sort of starting in the right place, getting something that's sensible, and then building it from there, I think is a really good approach. That's certainly things that we've done before. There's a blog here, which of the blogs on the website that say they were written by me, this one actually is, which is nice. So do feel free to have a look at that. It's a little bit old now, it's probably about a year old, but it just goes through a few of the things that we're seeing in this kind of space, because it's not just certainly not just the UK, not just the kind of areas that people in this room are working on. There's a lot of different areas that are that wouldn't have expected to be using AI, but suddenly they've found some use in an area that they weren't expecting. So there's some quite interesting